This is the last chapter of the ZONAIR training. And in this chapter, we're going to talk about aeroheating analysis. Okay. First of all, in the Mach car, you have to specify method 2 in order to activate the hypersonic aerodynamic method. We only need one car to perform the aeroheating analysis, which is called thermal. So you define a thermal bulk data car, and in the case control section, you specify a thermal case control command, and the integer match the ID of the thermal bulk data car. And the thermal bulk data car refers to aerogen car. Okay, and for rigid aircraft aeroheating analysis, or you can refer to put the ID arrow equal to negative. It refers to the flex LD. In this case, you are doing the flexible the air heating analysis on the flexible aircraft. And also you can replace the ZONAIR compute aerodynamic solution by a CFD, or so you using IMP CFD or IMP CFD1 car, and to replace ZONAIR compute implicit aerodynamic result. So the objective of the aeroheating analysis is to compute the heat flux on the surface at a given flight condition. The heat flux can be the input to a heat transfer analysis to compute the heat accumulated in the structure. The aeroheating method in ZONAIR uses the inviscid velocity components computed by the hypersonic aerodynamic method to generate the streamlines on the surface. Then a 2D hypersonic boundary layer method is applied along each streamline to compute the heat flux. So in other words, the aeroheating method in ZONAIR is somewhere between 2D and 3D method. So we call it 2.5D aeroheating approach. So the thermal car, you give ID, and this ID is referred to by the thermal case control command. And this one, if it's positive, it refers to aerogen car. If it's negative, it is referred to the flex LD bulk data car. So you can include the structural flexibility effect in this aeroheating analysis. In this case, you have to specify solution 1 and assign FEM to import the structural model solution. Then you have to do the spline. And temperature is initial surface temperature. Is a real number followed by a character, either F or C, attached to the end. For instance, temp equal to 200.0 F, which is 200 Fahrenheit. And if temp equal to 200.0 C, is 200 Celsius. And altitude, you give altitude, the length unit must be consistent with the length unit specified in the aeroz car. And hot wall equal either yes or no. If yes is a radioactive equilibrium boundary condition, the surface temperature defined in the temp entry is used as the initial temperature condition. If it's a no and it's cold wall boundary condition, the temperature on the surface is fixed at 10. Chance, if 0, and the program will automatically determine the transition from from laminar to turbulent flow. If 1, its entire flow is assumed to be laminar. If 2, the entire flow is assumed to be turbulent. And gas, 0 is ideal gas, 1 is ideal gas with helium, 2 is for real gas. Immiscibility, you use only for hot wall equals yes. The default is 0.8. And the stream can be either a character, string, or integer to define the aerodynamic panels whose streamlines are included in the plot file here. If all streamlines of all aerodynamic panels are included, if 0, no streamline is included. If greater than 0, it refers to a panelist 2. On the streamline from stagnation point to those panels are only included in the plot file. So the thermal bulk data count is referred to by the thermal case control count and to compute the aero heating result. This result including temperature, heat flux, skin friction coefficients, pressures, and the flow transition from laminar to turbulence distribution on the aerodynamic model. Every streamline starts from the stagnation point and ends at the control point of the aerodynamic panel. These streamlines are computed based on inverted surface velocity generated by the aerogen car. The aero heating results are calculated along each streamline using a two-dimensional hypersonic boundary layer method. Of course, you can use IMP-CFD or IMP-CFD1 car to replace ZONAIR compute inverted solution. So in this case, the CFD method must be also inverted, namely the Euler solver. So the aero heating results stored in the file include the aerodynamic panels with the CQA4, CQA3, and both up and low surface of the CL7 micro element, the pressure coefficient, the friction coefficient, the heat transfer coefficient, the wall enthalpy, the wall temperature, heat flux, the wall pressure, and the flow laminar transition turbulence region at the aerodynamic grid point are all calculated. And also, you can look at the streamline. So let's give you an example. This is called compact kinetic energy missile CKEM. The CKEM has all movable band nodes for control and 8 wrap around fins. The center body of CKEM is modeled by a body 7 car. It's a body of revolution. The band nose angle is modeled by the camper line of the body 7 Bogota car. Each warp around fin is modeled by 8 CL7 Bogota car to represent the curvature of the wrap around fin. The thickness of the fin is represented by the PA47 car. If the structural flexibility effects are considered, the solution 1 and the assigned FEM case control executive control command must be specified. You have to specify the spline input card, and the flex LD Bogota car is used to refer to the aerogen car. So you can calculate including the structural flexibility effect in the aero heating analysis. First, we want to validate the ZONAIR hypersonic aerodynamic results on CKEM and at Mach 6 with band nose angle 0 and 2 degrees. So the open square is the band nose equal to 0 from the test. Open circle of band nose equals 2 degrees measured by the wind tunnel test. And the solid symbol are the ZONAIR solution. So you can see the ZONAIR solution at different angle type from 0 to 6 for the lift. It correlates well with the wind tunnel data. And for the CM, and you can see at least at the low angle tag, it matches well with the wind tunnel test. And then we define a thermal count. And the thermal count with a negative sign here, so that refers to a flex LD car. Flex LD car refers to the aerogen car. And in the flex LD, the dynamic pressure is 370. And in aerogen car, we define the angle tag to be 6 degrees. And it will refer to Mach car and at Mach number 6. And then this dynamic pressure is at Mach 6 and altitude equal to sea level. And we define the initial surface temperature to be 80.33 Fahrenheit. And we hover equal to yes, so we use a radiative equilibrium boundary condition, and we want to calculate the transition from laminar to turbulence determined by the program. We want to use real gas, and the Aeroheating result and the streamline are output in the file called therm dot plot. So this the result, and this one is plot the surface pressure at Mach 6, angle type 6 degrees, dynamic pressure 370, and this the streamline, and this is the temperature on this CKEM. Then the next case is a hypersonic aerodynamic analysis on a 15-degree blunt nose cone. And we use the body 7 to model this cone, blunt nose cone, and we have a 44 actual stations. Each station will have 21 points around the body, and we define the nose radius to be 1.1 inch, and the I-axis is this round nose cone ends at the 43. So the thermal Bogota car is used refer to Aerogen car, where angle type equal to 5 degrees is specified. The Aerogen car refers to a Mach car, and with entry metric 2 for hypersonic aerodynamic analysis, and the Mach number is 10.6. And we can compare the inviscid surface pressure, and this the ZONAIR. This is CFL3D older solution, and then we can compute the CP on the inviscid at the 15% cone. So I think this is the wing side, and this is CP. The square, the open square are the wind tunnel measure the CP. The solid line are the CFL 3D computer CP. The plus is ZONAIR computer CP. Then we can calculate the laminar heat transfer rate at this flight condition. We also compare ZONAIR and CFL 3D plus the latch code, and we can calculate the Q dot, which is the heat flux compared to the wind tunnel test, and this the computed by ZONAIR, and the solid line is computed by the CFD. Okay, so this is the Aeroheating analysis, and this is the end of the ZONAIR training.